My name is Jorge Isaac, and my teammate is Isaac Ramirez. So today we'll explain the basic of image processing using the OpenCV on our Raspberry Pi 4. We will see how to manipulate pixels matrices and understand the math behind why the images look the way they do. So first we have image padding using the CV2 copy make border function. An image is just a matrix of numbers, and here we literally expanding that matrix by adding extra arrows and columns of pixels around it. So let's run. On the left, we use a constant border. We told the program to fill the new pixels with a specific beer RGB value, which is why you see a solid, uh, a light blue uh, frame. So as you can see here, it says 255 and 255. So here we have and on the right we use a replicate border. It takes the exact values of pixels at the very edge of the original image and copies them outward, which is why the edge look stretched. So as you can see here, you can see how the skin or the fur of the fox is stretched. So let's continue with the next program. Here. So next image blending is we simply add an image, the pixel value up to images together. The numbers quickly exceed the maximum limit of 255 and the image just turns completely white. To fix this, we create the CV2 add weight function. This function multiplies the first image by weight, for example, 0.5 and the second image by 0.52 before adding them together because we are averaging the pixels. The final value stays within the normal range. That is why the result looks like a smooth double exposure or transparency instead of a blown out white screen. Like you can see here is the bunny and the fox in one image. So let's continue with the next one. So we have the mathematical color inversion, negative. So our third code, we create a digital negative using basic matrix algebra. First, we convert the image to grayscale, meaning the pixel value now range from 0, which is pitch black, to 55, which is pure white. To create a negative, we simply subtract the entire image matrix from 2055. So a dark pixel with a value of 5 becomes 250, turning it bright white. A bright pixel with value of 200 becomes 55, turning it dark. We literally flip the mathematical values, creating this exactly inverted effect. I can see this is the inverted image of the fox, and this is the original image, but in a grayscale. So let's continue with our very last problem. So finally, we compare how OpenCV and NumPy handle memory overflow when adding pixels. Because pixels are 8-bit integers, they have a hard limit of 255. When we add a too bright image using OpenCV, it uses a saturation operation. If the sum is 300, it simply casts at the maximum limit of 2255. That is why the OpenCV image looks very washed out and mostly white. However, when we use NumPy, it uses a module operation. If the sum is 260, it resets back to 0 and starts counting again, resulting in a value of 4, which is almost black. That is why the NumPy image looks distorted and full of strange and noisy artifacts. So you can see here. So understand is this. Pixel math are critical for processing computing vision algorithms efficiently, and especially we prepare to calculate and other things for our future projects. So thank you, and let's see a little bit of the book with my teammate Isaac.
We're going to talk about the chapter 5. The name of this chapter is Basics of Imaging Processing. In this part, we use Python and OpenCV on our Raspberry Pi 4 to change images. First, we learn how to add a border to a picture. We put a solid green frame around the photo. Second, we mixed two pictures together. We made them transparent so we can see both photos at the same time. Third, we create a negative image. We change the colors to make it look like an old camera film. Finally, we learn how about pixel math. We add two images together to see what happens when the colors get too bright. And OpenCV makes the picture white, but another tool called NumPy makes it look very strange and noisy. This chapter is very important. It teaches us how to change pixels using math. This will help us a lot when we program the camera, and and that's all. Thank you.